Well, good afternoon, everyone, and thank you for joining us for a presentation on powering up your buildings. My name is Alex Strassenberg. I'm a senior mechanical engineer and partner with Pathfinder Engineers and Architects, and I'm joined by John Nickerson, who is a facility manager here at Alfred State College of Technology in Alfred. Our presentation also includes input by Corey Wilson, who is one of our senior electrical engineers with Pathfinder. Corey could not make it here live today, so we are pre-recording this and presenting this as a recording, but we will have folks available live at the end of this presentation to answer any questions you might have. So please feel free to ask questions and we'll be able to respond to them afterwards. So with that, I'm going to turn it over to John and let John talk to you a little bit about Alfred College.
Thanks, Alex. As stated, my name is John Nickerson. I'm Director of Facilities here at Alfred State College. For those that might not know, we're a small rural college in Western New York. Pretty close to the Pennsylvania line, south of Buffalo. I do want to start by stating that we are fully in favor of finding an efficient, clean, renewable form of energy to power up our campus. And I'm very happy to see SUNY taking such a strong stand to transition all campuses to be the most energy efficient college campuses in the country. This transition will have a long-lasting effect not only on our carbon footprint, but what our world will be for future generations. It will also allow SUNY campuses to be the leader in educating future generations to not only create this efficient energy, but also the folks to help maintain it. The efficient use of energy also leads into creating building envelopes that will support such systems. And there are many buildings in the SUNY system that just are not getting any younger and need these upgrades. This will also lead to the beautification and modernization of SUNY system campuses. Electrification of our building unfortunately comes with some downsides too. And being, as I said earlier, in rural America, one of the biggest is the quality and consistency of our electric service. Electric gets to our campus mainly through overhead lines that run through overgrown areas with a lot of old growth trees, and most of those areas have limited accessibility. This equals large scale and extended power outages when weather turns for the bad. There is the additional side to the power getting to campus, and that is the straight up capacity. Due to the reliability issues with the electricity coming to our campus, natural gas to all our boilers, domestic hot water, and heating is what is most common for us. To add these systems to our electric grid would increase our demand, and I'm not sure if our service could handle this increase in demand. That's just to get the power to our campus. We would then have to determine if the campus infrastructure could be sized appropriately to handle this. On-site generation is another way to meet some of the demands. Our geographic location is a little bit difficult there as well. While we have some beautiful fall colors and a gorgeous view over the valley, being built into a hillside really makes it difficult for any sort of a solar field or wind turbine. One of the last challenges I want to bring up is a bit more personal for us here at Alfred State College, is we recently decentralized our heating plant and went to satellite boilers. This was a large investment for us and is a little bit difficult to change quite this quick. We also are in the middle of investing some more into upgrading our generators on campus so that when we do have our power outages, more of our buildings come up. As you can see, Alfred State is very much in favor of creating a better tomorrow, but many challenges face us if electrification is the answer.
Thanks, John. And I think you touched on a lot of good points there. That I think that the specific thing is there's really going to be no one magic bullet on how we address this challenge that we have before us. And each campus is going to have their own unique situation based on their topography, their land that's available, et cetera. So all of these things are going to operate into a kind of an integrated approach to this, where we're looking at addressing building envelopes, on-site generation, and different types of technologies on how we heat and cool our buildings.
Welcome, and thank you for attending today. As we move forward with reducing our carbon footprint on our environment and developing our projects complying with directives such as SUCF 1B2 net zero carbon new building, and deep energy retrofits of existing buildings. We must also comply with regulations set forth by New York State to reduce greenhouse gases by 40% by 2030. Many of these regulations and directives are moving our designs to more energy efficient systems and our buildings to become fully electrified by our grid or renewable sources. As the requirement for additional power is needed by our buildings to reduce our carbon footprint, so will be the size of the electrical equipment, distribution, campus loop, emergency, standby loads, and real estate. As we dive into this topic, our learning objectives will be real estate considerations for electrical equipment in an all-electric design. How does electrification change the requirements for emergency, standby loads, and expandability? How mechanical system choices affect the electrical service size in real estate? And planning and implementation for today and tomorrow. Real estate considerations. As our need for additional power become necessary, there will be an increase in the size of equipment. To get a general understanding, we're going to use a 50,000 square foot building with average loads and some rules of thumb. In complying with the 2020 Energy Conservation Code, LED lighting would be around 0.8 watts per square foot. Devices, an additional 2 watts per square foot. Miscellaneous loads of 1.2 watts per square foot. And typical HVAC for gas-fired heating equipment and cooling adds 4 watts per square foot. For our typical 50,000 square foot building with the aforementioned loads, we would consider 400 kW total load with a potential power factor of 0.9. Our KVA would be around 450. Using round numbers, and the building would be supplied with a 500 kVA transformer and service. Now, taking a potential gas load of 50 BTUs per square foot and our 50,000 square foot building, the possible gas load would be 2.5 million BTUs. With a conversion of 3,412 BTU per 1 kW, a potential additional load of 730 kW would be added to the existing load of 400 kW for a total of 1,130 kW. The previous loads used were for gas-fired HVAC equipment. What is being added is the heating element. Motors will remain and cooling would remain from the previous 4 watts per square foot. When applying our power factor of 0.9, our KVA would be around 1,250 kVA, and the building will be supplied with a 1,500 kVA transformer. In comparing the real estate of a 500 kVA and 1,500 kVA transformer, it has grown from 90 inches wide to 108 inches wide, but the height and depth remain the same size. Additionally, the weight has increased from 8,200 pounds to 13,300 pounds. With the increase of your service size, other potential code issues arise, such as working clearances, additional sections of switchboard or switchgear for distribution, and the requirement for 2 means of egress on opposite sides of your electrical room. These egress requirements occur when your service is rated 1,200 amps or more and equipment length is over 6 feet in length. How does electrification change the requirements for emergency, standby loads, and expandability? As your buildings and projects transition to fully electric buildings, your code required emergency load for a typical building will remain about the same. NFP 101 sets the standards for level 1 loads and level 2 loads. Level 1 loads include loss of human life and typically are the need for emergency lighting and backing up a fire alarm system. Level 2 loads are less critical to human life and are typically your standby loads. Many of your level 2 loads are owner requested or by building type to maintain or protect your assets. As noted from our example above, a large heating load of 730 kW was added to the building This load does not consider any of the required level 1 loads, potential level 2 loads requested by the owner. In taking the building design's original design with natural gas, the load was 400 kW. If 60% of the loads are required to be backed up by an emergency generator, our backed up load would be 240 kW. But without calculating inrush current and starting across the line, we would potentially have a 300 kW natural gas unit. Physical 300 kW natural gas unit is feasible to be placed into a building or on site. Typical site-mounted unit with an enclosure is approximately 20 feet in length, 7 feet in width, 9 feet in height. Taking our electrified building with a load of 1,250 kVA and the same 60% backup required, that would be 750 kVA and potentially need an 800 kVA without considering inrush current or stepping. Many natural gas providers only make units up to 500 kW. This would force the solution to be a diesel-based unit. This unit has a much larger real estate footprint and could be placed inside of a building or on site as well. Typical 800 kW site-mounted unit with an enclosure is approximately 24 feet in length, 8.25 feet in width, and 10.9 feet in height, and will range an additional 1 feet or 2 feet in height with the required number of runtime hours necessary and fuel storage capacity. As your standby loads increase and your generator increases, there is still a need to exercise the units monthly and is recommended to be done under load or ran to a manufacturer recommended temp. This is done to eliminate any chance of wet stacking and damaging the engine. Many larger units will have trouble reaching the manufacturer temp without a connected load, and the necessity for load banks installed on these gensets will be required. In trying to stay with natural gas, eliminate larger units, and adding in some redundancy or future capacity, paralleling smaller generators is an option. In this scenario, the possibility of 300 kW units could be paralleled together to make up 900 kW of standby power and allow for servicing of 1 unit at a time while the other 2 carry the load. Also, if the load doesn't require all 800 kW at the time of an emergency and it only requires 500 kW, then all 3 would start. 2 would be brought online and then 1 shut down. If the load increases, the 3rd would start back up, come online, and parallel to carry the load.
Good afternoon. I'm talking to you from my office here in Rochester, New York. And as you may notice over my shoulder, I have an old gas pump, which maybe that is a metaphor for the topic that we're going to be discussing today. I think that we can all agree that fossil fuels are a finite resource. And while they may not disappear in the next 10 years or maybe even the next 100 years, as that resource depletes, the way that we operate our campuses with fossil fuels over time is going to become more and more cost prohibitive. So what can we do about this? I suppose we could just wait and not worry about it and let the next generation deal with this in their designs of the future. But I think a better approach is the SUNY approach, which is to be proactive in how we address our systems today and be ready for the time when the future comes. We want to be ahead of the curve and plan for these things in advance. Some of the things that we can do to be successful in this, and largely what's going to be successful in how we operate with renewables, is how we manage electrical demand on campuses. The way that we're going to have to address these systems is going to be a multi-pronged approach. And really the success of how we address them is going to be how we manage electrical demand on campuses. So we're already talking about these things today in our designs. We're talking about integrated design. We're talking about envelope improvements. We're talking about heat recovery and energy efficiency and HVAC systems. But the thing that we really have to think about is how buildings of tomorrow are going to be operating. And a good example of this is going to be on our heating systems. Today, it's not uncommon to heat buildings with 180 degree or 200 degree water. It's a simple thing to do. We can use small pipes, small coils, etc. But as we transition to renewables in the future, our sources of hot water are going to come from compressorized systems, things like heat pumps, refrigeration type systems. And those type of systems can only generate 120, 130-degree water. So a simple thing that we can do today in our designs to anticipate the operations of buildings in the future is design systems with deeper coils, maybe a little bit larger piping, the ability to move larger volumes of low temperature water to heat and cool spaces. Those are some simple things we can do. And the beauty of this is that a lot of campuses already have transitioned from central plants to multiple modular condensing boilers. This transitional technology operates at its highest efficiency at those low water temperatures. So we can connect these systems that are designed for tomorrow to our existing condensing boilers and get the most out of them today. Another thing that we may want to consider in HVAC design is transitioning away from large central systems to smaller, more modular equipment. Things like heat pumps, fan coils, high performance hydronic systems like chilled beams. All of these types of systems are going to give us greater flexibility in how we manage electric demand in our buildings. Smaller systems can be duty cycled and they can be brought online incrementally to address building perimeter loads and skin losses. Also, the thing that smaller modular systems do is they allow us to take the ventilation out of the HVAC equation. And this is going to be especially important when we're dealing with buildings that may be operating under standby power conditions, is the ability to take that large ventilation load out and not cause extra stress on our generators or grid. Some other things that we may want to consider is revisiting old technologies. Back in the 80s and the 90s, I remember when ice storage was the great rage, and a lot of the driving force behind ice storage was to reduce utility costs. Often buildings and building owners would put in ice storage systems, and the idea was to generate your cooling needs at night when your utility rates were very low. You could run your chiller from 9 o'clock at night till 6 in the morning, build up a thermal storage of ice in some tanks, and then ride that ice storage during the day with your chiller off to help cool your spaces. This type of approach may have some new acceptance in the renewable world. It's a concept that may help equalize the use and demand on the grid throughout the course of a day. Advances in heat pump technology are still occurring today. The ability to couple heat pump technology with ground thermal storage systems can help campuses address their simultaneous heating and cooling needs in a very flexible manner. And finally, I think the one thing that we're going to have to do is maximize the use of our energy management systems. They're really going to have to be looked at as an entire campus management system, more than just building by building. I think the ability of having this intelligence at your fingertips, the ability to see how each building operates individually and the campus as a whole will allow us to cycle buildings on and off, cycle on smaller modular systems, and maximize energy use while minimizing the demand on the grid.
Planning and implementation for today and tomorrow. In planning for the future, it's a vision that at times can be very vague and undefined. With changes to the codes and directives done by state and governing bodies, the target is always moving. When planning, consider providing some additional space to your electrical rooms. Everyone likes to maximize the available space and squeeze everything into a very tight area. Where possible, provide dual entrances at each end of the electrical rooms to comply with larger equipment. Provide additional clearance in front of the equipment and around all sides. Additionally, if the building allows it, provide separate service entrance equipment for overcurrent protection, transformers, and secondary distribution in lieu of one lineup. When planning for standby loads, whether the generator is inside of the building or an exterior unit, and the generator will be supporting electrified heating loads in the future, controls for future paralleling can be considered. Additional real estate and pathways can be put in place, especially if the generator will be placed outside on the site. Interior space should also be considered for transfer switch equipment and distribution. Again, it's hard to predict the future, and your current projects may not be full renovations requiring electrified HVAC systems. But with current projects that are replacing equipment due to failing or at their end of life, some considerations for the items we have discussed today may help in the future.
Alex, I do have a couple of questions for you. As I mentioned, we decentralized our central boiling plant and went to satellite boilers. This put a lot of boilers into the campus. Is all of that work lost, or would we still be able to use some of that?
No, it's a good question. And you're not the only campus that's done that. A lot of campuses have decentralized, they've shut down their central plants, they've gone with satellite boilers. And really the beauty of that system is it's going to help your transition to a renewable source of heating and cooling. As we talk renewable heating, renewable cooling, we're probably thinking of systems like heat pumps, refrigeration-based systems that are going to produce hot water heating temperatures in the range of 110 to 130 degrees. So one of the things that we can do is we renovate buildings, as we improve their envelope, we put better glass in. We're also going to be looking at how we design our systems. We're going to be designing systems with deeper heating coils, maybe taller sections of fin tube, systems that are going to be able to effectively heat and maintain your buildings using lower source temperatures of water. So the beauty of having satellite high efficiency boilers is that's where those boilers really perform at their best. That's where their peak efficiency level is, at those low temperatures. So we can design our buildings today to help that transition occur with the systems that you have in place, and they're going to be operating even more efficiently than they are probably today in the next couple of years.
That kind of leads into this next one. These types of changes and upgrades, what does that bring about from a maintenance and operations standpoint? Will my same heat and plant guys be able to work on this stuff?
Well, I think so. It's going to be change is always difficult. And certainly the types of systems that we're looking at are probably going to be a little more complex than what you've been used to in the past. And I think you have some of those systems even today on your campus. I think your life sciences building uses kind of a hybrid approach between ground source heat pumps, some chilled water, some chilled beam, etc. And the way I used to think of it is, I did a presentation a couple of years ago at the PPAA, and I was talking about cars. I'm an old car guy, so I talked about maintaining an engine on a car. If you look at an engine in a Model A Ford from the 20s and the 30s, it's really not much different than an engine in a modern car. The only difference is how much ancillary equipment that's been added to that engine. There's, instead of an old carburetor, now we have fuel injection. We monitor the amount of air we bring in. We monitor the amount of fuel we bring in, and we control it at a very precise level. And so the mechanics that we used to use 50, 60 years ago, you take your car to a technician today. And that's really the type of change I think you're going to see, in the capabilities of your staff are going to have to be trained to be more like technicians as they maintain the equipment and less like mechanics.
That actually brings on another question, if you don't mind. The electric side of it, is it easier to monitor through a BMS, or is it a little more difficult? More points, or do they all make more sense at this point?
I think you're probably going to find that the amount of BMS points are probably going to be similar. I think what you may find is that how you utilize that information campus-wide may change. I think electricity is going to become a very desirable resource, is going to become a very precious resource. Your demand, you're going to have to watch your demand on campus to keep the costs down. And especially if you had, as you mentioned, a power outage event, you're going to have to carefully monitor how you're using your on-site generation to maintain buildings on campus. So you're probably going to be using your BMS system not just to monitor what systems are running, but you may be able to duty cycle systems and operate portions of this building here and another portion of the building there, just to keep your buildings at the correct temperature during a power outage event, but to also be very careful on how you're utilizing electricity and not exceeding your demand capabilities of the campus.
Thank you.
Thank you very much for joining us today. We're going to follow up with questions and answers after this. John Nickerson and I will be available, as well as Jason Suss, to answer any Q&A that you may have.